Okay, so what I want to talk about now, I don't have that long to do it, is music alignment, and in particular, this also plays into the same kinds of things. Some of the techniques we use for trying to match cover versions, different performances of the same piece. So, because of the nature of music is that there's the idea of a composition, some, maybe a musical score or some composition that someone remembers, and then there can be multiple renditions of that composition. So you could think of the audio as a different version, a different representation of the piece of music, and then you can have different audio versions for different people playing a piece of music. And sometimes we're interested in comparing those things, and one of the things you might want to do is match them up, so you can figure out which part goes with which, rather than just saying this whole score goes with this whole piece of audio. One of the ways that this has been turned into application is this, which is this was Frank Kurth and Meinhard Müller and some people in 2007. They built an application that it would take a recording of a piece of music performance, it would take the score, and then as the music is playing, it highlights where in the score is being played. And so it's the problem of figuring, once you've figured out what the notes are in the score, where do they actually occur in the audio? And there are a bunch of nice applications for that, yeah.
So would that just give you one recording and one
so the idea is this is animated, right? So this little red box moves along during the recording to show you where it's being played.
But they just gave you the recording, right? It's not like you can just bring this other Beethoven recording and give it to it, and it'll show you where it is.
The idea is it was given a recording and a score, and it matched them up. If you gave it a recording of some other piece, and it wouldn't make it work. You could imagine doing that, right? So you could imagine a system that tries to do this, but has a lot of different scores, and tries to do it each one and has some measure of how well it matches, so it can maybe also identify the score and do that. I bet that's viable, but that was not the problem they were trying to solve here. That would be something else. It's a perfectly sensible thing to do. Okay, so they were doing it for scores. There's another thing that people have done, which is kind of cute, where you can take a particular piece and maybe it's been, some famous piano sonata that's been recorded by lots of different pianists. You can take all their recordings and then you can figure out, you can align them mutually. And I saw this application that I think Simon Dixon from Queen Mary in London did, where you can switch between the different performances. So you can have it playing along, and you can switch pianists, and you can hear exactly how their performances vary at each specific point within the music. And the point is that, of course, in general, if you play those pieces of music together, they'll drift apart because they won't be on the same time base. And so it's figuring out how the time in seconds relates to the point in the score and lining those things up. Another thing you might want to do is, if you have different recordings that you actually want to play together, you might want to actually align them. Not clear why that would happen, but sometimes if you've got some weird situation where you've got a vocal line which doesn't line up with the backing track, you'd like to realign them so that, because you've changed the backing track, you might want to align them like this so you can remix them with a different backing track. And then this task here, where they're figuring out how the score relates to the audio, this is nice because now suddenly if you say, well, transcribing the notes in the audio is hard, but I know that the audio is just a recording of the score, so now if I align it to the score, then the score tells me what notes are present. And so you end up with a ground truth transcription for that piece, or a pretty good approximation of it, which is useful if you want to do some machine learning on it afterwards. So a lot of the work in alignment is based on this similarity matrix. There was a very early paper by John Foote in 1999 which sort of described this idea, but it's just the frame-wise similarity between every frame in two different time sequences, and so that gives you this outer product type representation where now, here's one signal, one set of data, and here's another set of data, and then I just compare, times 16 from this one against all the times here, and I get a set of values. In this case, the representations I'm using here are beat synchronous chroma, right? So it's the time base is in beats, and then the representation is these 12-dimensional chroma vectors. And the things I'm comparing are two versions of Let It Be, the Beatles and a cover by Nick Cave. Let's just listen to Nick Cave's cover.
When I find myself in times of trouble, Mother Mary comes to me, speaking words of wisdom, let it be.
So the point is, it's very recognizable, right? It's obvious, we know which track that is. But it's quite different from the original. The instrumentation is different, right? There's piano in there, but it's mainly the guitar that's carrying the chords. And also his vocal delivery is different. So he's singing a slightly different melody, different timing, which is, typical for this kind of cover version where it's like, there's no point in singing it. Everyone knows the original. There's no point in singing the original. So you try and do something different to make it more interesting. So it's, and what we see here is these white blocks this is a Euclidean distance. So a small distance means frames that are pretty similar. So here's the C major chord at the beginning, and yeah, they're pretty close. But then, it's not that great. Also, these blocks, right, saying, well, the first 4 beats, which are the C major, there's pretty good similarity between these 4 beats and these 4 beats, but actually aligning within the diagonal, like there's no big distance between the match between the 4th beat and the 1st beat. So there's like these large blocks, but then where there are chord changes, you get smaller blocks lining up. When things match, you look for these diagonal stripes in these similarity matrices. The intro is pretty good. After that, when you get into the actual verse, the match here is not working so well under this representation. Yeah.
Does the normalization account for both time and pitch?
So, by using beat synchronous chroma, we're trying to normalize out the tempo. So if it's one is fast, one is slow, okay, we're just counting beats, so it doesn't matter. And then by using chroma, we're trying to normalize out the instrumentation, so piano, guitar, doesn't matter. But if he transposed it, if he'd sung it not in C major but in something else, then this would have not worked at all, right? Because now we're just doing the Euclidean distance between this 12-dimensional point and this 12-dimensional point. The fact they would match if we shifted them over one doesn't work. What you typically do, though, if you're trying to do this, is you maybe try and estimate the key of the whole piece. So you look at the distribution over this whole thing and say, well, a lot of C's in here, so it's probably in C major, and maybe in this one the most popular note is D, and so then you rotate everything down so that's taken out. That's kind of crude, but it turns out that it's normally pretty easy to get the normalizations right for key changes like that. The distance, you can use, and obviously you can use different distance matrices, different distance measures. If you think the data really are going to be very similar, you can use Euclidean distance just as distance between 2 points in 12-dimensional space. If you think they're going to have similar profiles, but they might be scaled by different amounts, if one was the same vector but just scaled by a half, so it was, the peaks were lower, then the Euclidean distance would be large. But the cosine distance is basically you normalize out by the amplitudes of both these things, and you take the inner product between them. And this is the cosine of the angle in between them in 12-dimensional space. And then 1 minus that gives you a distance measure, cosine distance, which is often useful. Yeah.
So is this kind of like a similar or same process that you would use for or the applications that SoundHound or something, where they tries to match?
Okay, SoundHound does several different things, right? But the Shazam thing, which only matches the same recording, They could do it like this, but what they do is actually much more efficient because they don't have to normalize out tempo or pitch. They assume that the tempo, that the recording is the same, and so that you don't, you can assume. Some of them try and take into account the fact that sometimes music played on the radio will be sped up by a couple of % just to make it shorter. But yeah. But basically, they're relying on the fact that it's the exact same recording, so that you don't need to normalize out these things. And that's why when you do Shazam, it can distinguish between different versions of the same song. It doesn't get confused. Listen to the Nick Cave and tell you it's the Beatles. It would never make that mistake. SoundHound also does query by humming, which is a much even tougher problem than this because there's very little resemblance between the query and the original. But they do that by a different way. So this is, this is mainly for cover song matching, which is not tremendously important commercial application, but does have some relevance. If we played these things are not aligned, so if you played them together, they would drift apart. We wouldn't hear them playing at the same time. Okay, so once we've got this matrix of similarities, that thing, and we're trying to find these diagonal stripes, we can use dynamic programming, like in Yaqing's presentation. We went through dynamic programming before, the general idea that you have these allowed transitions and you're trying to minimize the cost, which you can do recursively. This is a nice picture because it sort of shows a little bit about how that works. So here is a similarity matrix. It's actually, I don't know where it's from. I think it's a real one. But the idea is, at every point, you calculate the cost, the minimum cost of the best path. And the best path involves, every time you go through a cell, you accumulate the cost corresponding to that cell. So here are the costs. And so here, this first cell has a cost of 0.1, so all the paths that go here are 0.1. This cell has a cost of 0.2, so this path going to here has a total cost of 0.3, goes up by 0.1, etc., as you go down the path. This red path is the best cost path to this point here. But we don't necessarily, this may not be the destination. If we wanted to get to this cell, then here's the best cost path to that cell, which turns out to be down here, right? And the point is that in dynamic programming, you go through these cells one by one. You look at the preceding 3 cells, you figure out the lowest total cost of the cost to that point and the transition. And then you record, you take the smallest one and you record which one it came from. And so by the time you've solved it, you end up with the lowest cost paths to every cell on the grid. And then if you say, okay, and I was trying to get to here, then you trace this back and you get the answer. But sometimes you might say, well, actually, I don't care where I get to. I just want to get somewhere where there's a low cost. And maybe you'd rather get to it here with less of your vertical axis being used. And so you can do that. So there are a lot of variance on this depending on, the idea of calculating this entire matrix is the same, but then where you choose your traceback from can give you different answers depending on what you want. But also when you draw it like this, you can sort of understand that, well, there are all these paths out here, but they all resolve back to this path here. And that gives you an idea of why the dynamic programming allows you to solve this so efficiently. You calculate this cost once, and then it's used as the basis for calculating all these forward costs. Okay. So that was... So one thing we can do is we have 2 audio versions of the same recording, and we have this sort of chroma and some distance measure. We can try and align them. And so this was a little cute thing I did a few years ago where I would take cover versions of Let It Be or even some other tracks on YouTube and then try and align them. So you get alignments for the audio, and you can also align the video. And so this is like one of the most extreme contrasts, which is the original Beatles versus this rendition apparently by the Russian Navy choir. Let's see. And then to get the audio, once I've got the timing, I actually used timescale modification to scale the audio so that they would stay lined up, right? I'm stretching this dynamically, depending on the path. And then sometimes you'll hear some weird kind of buzzing because it's like repeating segments, which is a horizontal line. Okay. You get the idea. So, again, they had enough different tempo that by this point, if we just played them together, they would be totally unaligned. But you can line them up for whatever reason you'd want to do that. So that's audio to audio. Another thing you might want to do is audio to score if you have something, a digital representation of the actual notes. So let's say a MIDI version, and you can try and do the same thing. So this is the spectrogram of the audio version, and then the red boxes are notes from a MIDI version, a MIDI rendition, which again were aligned using this kind of dynamic programming alignment. So now what I'm going to play is the Beatles, and then on the other speaker, the MIDI version. So again, you can hear the notes lining up. It's hard to tell at this point, but that you can hear some other notes in there. So the MIDI version doesn't have vocals; it just has some lead instrument playing that, so you can hear them lining up. And so this is actually really nice when this works, if you have a good MIDI, because now, you can use this to actually figure out where these notes are, and it's you can use this for source separation type problems. There's a bunch of work been done on score-informed source separation, where if you have the original music mixture, multiple instruments, but then you have the score, you can use that to try and separate out the individual instruments, the original acoustics. So how do we do something like that, where rather than just matching the audio, we've actually got two different representations. Right? We've got the audio on one hand, and then we've got the set of notes, the score on the other hand. One thing you can do is, take the MIDI version, synthesize it to audio, and just match audio to audio. But that sort of seems to be a little bit crude, like you don't know exactly how you should synthesize it to make it most similar. There was this nice approach that some guys at EarCam, Oreo and Schwartz, came up with, where they defined a different distance measure which was specifically for this problem. They called it peak structure distance, and the idea was that if my MIDI tells me that I've got a particular note present, like a C3, well, I know that the audio C3 will have harmonics at whatever it is, 260, 520, 1040 hertz. But I don't know what the ratio of the energy of those harmonics is going to be. So if I just synthesize it, I have to choose some set of values for those harmonics, but it's not going to exactly match my original audio. The idea that they came up with was to say, well, I don't know where the energy is going to fall within these harmonics, but I expect energy to fall in these harmonics and not elsewhere. And so what they do is they come up with this mask which says, well, here are all the notes that are present, and here are the principal harmonics of all those notes. Now I'm going to calculate a ratio of how much energy the original audio signal falls under this mask to how much doesn't fall under this mask. And then even if the harmonics are some unknown ratio, as long as they're where the mask says they should be, then it doesn't matter where the energy is within the harmonics, it just has to be within those harmonics. And if there's energy that doesn't fall under that mask, it means that I'm seeing evidence of other notes of different harmonics present, which I can't explain. And so that allows you to come up with a distance measure. And basically, you're looking at the energy that's passed by the mask compared to the total energy, or equivalently compared to the energy that's not passed by the mask. And that gives you a new distance measure, which you can plug into your matrix. And that was actually what I used for that example with Let It Be. Okay, so now we know something about trying to line up these things that we have similar versions of. The natural thing to do this with is matching cover songs. And so this is sort of a task that became interesting a few years ago, and it was made up, basically. It was the people who were running these evaluations were looking for a task they could evaluate, which would force people to try and get at the musical information, the notes and chords, rather than just looking at instrumentation and genre. And so it was, they came up with a data set of cover songs, and then there have been evaluations on it for a number of years since then. And so the way you can try and do this is to do this sort of audio-to-audio alignment, and then for all the tracks, see if you get a particularly good alignment between them, and if so, they are showing evidence of being cover versions. But again, it depends on the representation, depends on the measures that you use. So one of the problems with cover song performances is that they're not going to be exactly the same audio from start to end. Music has this structure. It'll have an introduction, verse, chorus, different things. And one of the things that will happen in a cover version is that those things may be moved around. Maybe they'll, the covering musician may put an extra introduction on, or change the number of verses, or do a bunch of different things. However, there'll probably be chunks in there which match well. So the verse may be more or less identical, at least in terms of notes, but it may occur at a different point within the song. So what we want, the dynamic programming sort of has to find a single path from start to end. And so if you can't make a single global correspondence, then it's not going to work. This problem comes up in other sequence matching scenarios. So one of the big areas where they try and do sequence matching is in genome or genomics, where you have sequences of base pairs, and you want to find matching sequences in other species. And there'll be small differences, and you don't know where they're going to occur, but if you have a bunch of base pairs which look kind of the same, then you want to find them. And so there are some people in that bioinformatics area called Smith and Waterman came up with a variant of dynamic programming, which rather than just always taking the previous cost and finding the best transition, you take the previous cost here, you have the local cost, and you have some penalty score here. But if this value, or if this sum goes below 0, then you stop it at 0. So basically certain paths will have more and more cost associated with them, which you're subtracting off. So the things are getting more and more bad. But if they go below 0, you just say, well, okay, that's our baseline. We don't care about what happened historically. At that point, we're just going to start from nothing. So the idea is that now in this kind of Smith and Waterman surface, there are these planes out here where the cost has gone to 0. It's actually now a score. The score has gone to 0. But you can always start up a new match from anywhere within there. It's not like, it doesn't matter how you got there now. This is just starting from scratch. And so the idea is if you do have something which has no prior resemblance, but then suddenly starts looking positive, then you get these sort of building up, these ridges that build up. And so you have a penalty score here. If the penalty is saying that they're lining up, then it's going to be smaller, and if they're less good, then it's going to be larger. And so the trick is that the local match has to exceed the penalty, and then that'll sort of build up and sum up. If it doesn't, then you go down to 0. But when it does, you get these little ridges or patches building up. And then what you do after you've done that, rather than just looking at what happens at the very end, you just look over the entire matching surface and you say, well, what was the largest value it ever got to? And that largest value is at the end of the longest best matching streak. But it's kind of a trade-off between the length of the streak and how well it matches. And you can find subregions that match without assuming how long they're going to be, or where they are, where exactly they're going to align locally. This is a nice approach, but it's quite sensitive to these values. Because basically, if you make the reward for an on-diagonal too large, then these things build up very quickly. If you make it too small, then you may never build them up. So there's no good way of choosing these values. It just has to be done empirically. But in a well-behaved data set, it can work quite well. Smith and Waterman were working with these base pairs, and so they could set these values in a very principled way. They knew what should match and what shouldn't match. In audio, you don't normally have such well-behaved pairs. But this was used in this a very successful cover song matching system by Joan Serra and Emilia Gomez. They basically did what we'd expect. They took some kind of chroma. They have a particular kind of chroma, but it's basically chroma matrices. They figured out the transposition here, so they compared the overall chroma matrices of the two songs, then figured out what the best transposition would be for the whole song. And then then they calculated a similarity matrix by comparing the chroma of individual frames, which might look like this. But what's interesting is they then thresholded it. So they had some way of deciding yes or no whether these pair of frames match or not. And then they did the Smith-Waterman type dynamic programming alignment. By making this a binary matrix, they then also gave it so it had these reasonably well predictable match characteristics, so they could tune the Smith-Waterman parameters to make it work well. If you tried to do it directly on the Euclidean, then you wouldn't find a single set of values that would work for every time, because it sort of depends on how similar the instrumentation is. But if you can make it so that you can normalize out all that and just have a 1-0 match, then it works much better. I spent a long time looking at this algorithm trying to figure out why it works so well, and there's obviously more going on, but that's one interesting twist on it. So here's a system that I put together for cover song matching, which is kind of different. One of the things I was thinking about was trying to do this in such a way that you could have a very large database of tracks that you could match without having to do a dynamic programming alignment between every pair, because that's quite a lot of computation. If you could have something which only depended on Euclidean distances, then there are very fast ways for calculating Euclidean distances between points in large databases. And so that's what I was trying to come up with. And a Euclidean distance, you can calculate Euclidean distance by cross-correlation. You can calculate at every possible offset or something like that. And so the intuition was, you have the query, you have a bunch of little patches here, and then you figure out how similar those patches are to every point in your reference item, which you can do by cross-correlation. But in principle, you're just comparing it, doing a local comparison of a block of values at every point. And that even if the whole track doesn't line up properly, if there's one little block here that lines up well, then you'll get a high score, and then you just look for some particular points that score well like that. That's, to deal with this idea that we don't expect the whole track to line up. But then it turns out that, well, if you have, how do you decide how big your patches are going to be, etc.? If you do the thing that looks like you're trying to match the whole track, so if you just do the cross-correlation between the entire matrices, then if there is one patch in here which lines up well, there's going to be some alignment where you're going to get those things to line up. Now, you're also going to add on the alignment of everything else, but if that's unrelated, then it's probably going to just basically cancel out. So even though you don't expect the whole thing to line up, or you don't assume the whole thing's going to line up, just simply cross-correlating it which will mean that at some point you have the best patch lined up as best it can, and then all the unaligned stuff will sort of tend to give you a negligible additional contribution, so you sort of don't have to worry about where it is. So that was my system, and it sounds like you've missed the point about the fact that the structure's not going to match, but it works out that it doesn't. You still get the effect you wanted. So this is the cross-correlation. We cross-correlate this is the time difference, the lag in beats. We cross-correlate in 2 dimensions, so we also have a cross-correlation on the frequency axis, which is basically transpositions. So by doing a 2D convolution of these things, I end up testing all possible time alignments and all possible relative transpositions, the 12 plus or minus 5 or 6 semitone transpositions. And you end up with these spots, right? So here, obviously, when the transposition is wrong, you don't get any particularly good alignments. But when they're at the correct transposition, in this case, it was like there was a tone difference, so it's plus 2 semitones. you see this, now you look along time. So this is this slice along time. And you see that there's a general trend for it to have more correlation in the middle than at the edges. And that's just because these chroma things are non-negative, so the more they overlap, the more chance there is for them to sum up. And if they're highly skewed, then they just don't have so much overlap, so you have less underlying total accumulated in a product. But here's this very sharp alignment peak, which corresponds to suddenly a bunch of beats line up, and then when you move them, they become unaligned. And this is the feature that shows you that there's a match in the actual chroma structure here. And you see there are some off beats here, off peaks here, which correspond to the repeats in the music. Yeah.
Are these after the files have been compressed at the same time, like scaled to the same?
This is on beat synchronized chroma. Yeah. So the other, if they weren't on that normalized beat synchronous time base, this wouldn't work. This would be much less likely to work. Right. And so one of the problems with this, most people, empirically, beat synchronous systems haven't worked well for cover song matching. And the best explanation for that is that the beat tracking introduces enough errors that it overwhelms your advantages. So if you get the beat tracking wrong, it's not going to work. One thing you can do is you can have multiple different beat track hypotheses and have them all separately inserted. So you might try a couple of different tempos, but it's still a problem. This overall bump in the correlation you can get rid of just by doing some kind of high-pass filter on this. So this green is just the high-pass filtered version of this correlation. And so now you only keep the rapid variations, and now this is the single greatest peak. What's interesting about that is that we got this cross-correlation by convolving these two things together. We time reverse one of them and convolve them. And so we're taking the cross-correlation, then filtering, which is the same as doing, because cross-correlation is convolution with a time reversal, it's still linear. You can actually do the filtering first and then do the cross-correlation. And what that filtering would mean would be to look at the time differences of the chroma matrix. So rather than looking for when the chroma is on, we just look for when there are changes in the chroma, when it goes up and when it goes down. And that's actually quite a nice, that sort of makes sense, that what matters about the chroma is where the notes change, where the note onsets occur, not so much what notes are present. So I have my own little test data set. I have this big database, or this reasonably big database of about 9,000 tracks called US Pop from a few years ago. And I manually went through looking for cover versions in that. I basically sorted the tracks by title and then looked at songs that had the same title. I had to listen to them, right? I didn't know all these tracks. So it was basically subjective labeling, but I came up with only 23 matching pairs. And then for this, so there was 23 songs with 2 versions of each. And then these are this is the best covers, and so I find that I'm getting about half of them right, and I'm getting these decoys, these mistakes they're making with the off-diagonal red dots. What's interesting is that there are certain tracks that tend to get picked a lot, right? They tend to have a high score against all different, all the matching candidates. And this is to do with normalization by the total size of the number of tracks, or the total number of chroma events that you can play with to try and make it work better. This is just saying that if you do have this thing which is correlated over the entire matrix, you can actually analyze to see, how good was the match at different points just by taking this correlation and summing it up over frequency first and then plotting it as a function of time. The overall best match was the sum of all these values here, but you can see that the contribution differs by different time periods, which can indicate where the match was strong. This is an example of a false alarm. I don't have time to play it to you, but it turns out that the vamp in Cocaine by Eric Clapton is actually a pretty good match to the vamp in Satisfaction by Rolling Stones. It's so that's why it gets this one wrong. Okay, so that's what I wanted to. What we're going to do on Wednesday is we're going to do some stuff with trying to match tracks based on beat chroma matrices. But rather than analyzing them all ourselves, we're going to use a pre-calculated set of analyses, and they actually come from this API that the Echo Nest provides, which is this. They're a company that does music informatics. They were set up by a former student of mine. But one of the things they have is this system where you can upload a WAV file and it'll run all these things to calculate various analyses, which you can use for matching. So it's kind of it's not that different from what we could calculate for ourselves, but it's just nice. It's interesting to have it as something you can run offline. But I'll talk about that more on Wednesday. Any